Hi there, my name is Miss Townsend, and I love math.
This video is for students in Functions and Relations studying the year-end summative. It's question number 15.
It says, you wish to retire. Oh, that's a typo. You wish to retire. I don't know if you can see my brush here. There we go. You wish to retire with $1 million when you reach 60 years of age. Good idea. Determine the present value of this money, assuming you can earn 7% per annum, compounded monthly from now until your 60th year. Whew. Okay, so we're obviously going to need to talk about some financial equations. So here they are. Um, when it says determine the present value, so what we're going to do is we're going to assume that we will put a certain amount of money into an account and come back in when we're 60 and spend $1 million. Sounds like fun. Excellent. Now, of course, if I do this question for me, I'm a little bit older than you, so it would be a very different number. So I'm going to pretend for a minute that I'm, oh, let's say 17. Woohoo! So if I'm 17, how long is this money going to sit? It's going to sit for 43 years. Okay. So we're going to put an amount of money into a bank account for 43 years. What else do we know? Well, we know that it's going to be compounded monthly. So if it's compounded monthly, then we're going to need to adjust both the 7% interest rate. So we're going to have to make sure that we divide that by 12 to represent the monthly. And we're also going to have to change the n value because it's 43 years and 12 times a month. So both of these things are going to have to get factored into our equation. And the other thing to remember is that we have the future value. We know that we want $1 million, and we're trying to figure out the present value. So here's what all of that looks like when I do sub it into the equation. So $1 million right there. It's nice to write. It's even nicer to spend. Not that I would know. So we want to know the present value. Um, so my interest is 7%, but it's cut into 12 pieces because it's compounded monthly. And my 43-year time period is actually multiplied by 12 because it happens every month. So again, that monthly impacts both this number and this number. So let's see how much of this we can calculate. So $1 million. Boy, that's an old reference. So this is going to be 1 plus, and I'm going to try to save as many decimals as I can because when we're dealing with financial stuff, I want every penny. So this would be 1 plus, hold on, 0 point, oh, no it's not. It would be 1 plus 0.00583, and that would be to the exponent 43 times 12, 516. So let's do that calculation. So my unknown is right here. That's my unknown. So I'm going to calculate all of this and save a whole bunch of decimals, and then I'll isolate my unknown. So 1.005833 to the exponent 516 equals, so what do we get? We get that $1 million, 1, 2, 3, is the present value times 20.1073. So to find the present value, I need to divide by 20.1073, 20.1073. So what do we get? $1 million divided by 20.1073, and I get 49,733.14. So that means if you today could find a bank account that paid you 7% per annum, compounded monthly, and you could find $49,733, leave it in the account, walk away, don't touch it, and then come back when you're 60, you'd have $1 million. Sounds pretty good. Of course, where does this money come from? That's another story. Um, so that was the first part of the question. And the second part says, assume you do not have enough money to invest today. So let's just pretend for a minute that you don't have 49,000 sitting around. What monthly payment would you need to reach the same goal? So in other words, instead of depositing a lump sum of $49,700 and walking away, what you're going to do is you're going to deposit a certain amount of money every single month until age 60. And when you are 60, that when you turn 60, you're going to go and you're going to say, "Hey, look, I have $1 million." So this is now a monthly or an annuity. So we need to find the formula where there's a future value and regular payments. So this is the formula I want because this is where I amass regular payments plus interest to achieve a certain goal. And that goal, again, is $1 million. And we were told to use the same compounding period and interest rate of 7% monthly. Okay, so let's go ahead and set this up. So the future value, or $1 million, is equal to, so the regular payment, I don't know it. So this is going to be 1 plus, and it was 7%, but it was monthly. So I'm going to get a bracket around this. And the exponent was 43 years, but again, monthly, minus 1 bracket. And I need to divide this by my interest rate, which is 7%, but again, it's monthly. So that's the math I have to do. Now it looks like a lot, but just take it in turn. Don't get ahead of yourself. Is that a million? Sure. So there's R. So in this bracket, so I have 0.07 divided by 12 plus 1. So let's figure out what that is. And I've already done it on the other question, I realize, but whatever. Divided by 12 plus 1, and I get 1.00, sorry, 1.005833 to the exponent. And what was this number again? 516 minus 1, and that's going to be divided by, and again, 0.07 divided by 12, that's this 0.005833 number. So $1 million equals R times, so I'll take 1.005833, and I'll put that to the exponent, 516 equals, and then immediately subtract 1. So I get 19.1073, oops, and that's divided by 0.005833. So now I'm going to do these things here. So that R is multiplied by 19.1073 and divided by 0.005833. So I'll do those two little pieces of math. So 19.1073 divided by 0.005833 gives me, so here we go, $1 million equals R times 3275.7243. So to solve for R, all I have to do is divide by this number. So on both sides of the equation, I'm going to divide by 3275.7243. So divide this by 3275.7243, and that'll tell me what monthly deposit needs to be made. So $1 million divided by 3275.7243, and that gives me $305.28. So if starting now you had $305.28 and you found an account that paid you 7% interest per annum, compounded monthly, and you every month for the rest of your life until you're 60 deposited $305.28, when you're 60 you'd have that lovely $1 million. And if you do that, why don't you look me up and give me some of it for, helping you do the math. I'm not kidding. All right, thanks for watching. Bye.